Hello, everybody, and welcome to this week's Future in Space Astro Coffee Hangout. We've got too many hangouts going on. My name is Tony Darnell. I work at thedeepastronomy.com, and this week we're going to be talking about black holes, in particular some research that was done with NASA's NuSTAR spacecraft to look at a particular black hole that is spinning, and in fact it's spinning in an unusually fast rate. So we're going to be talking with the authors of that study here in just a moment. But before I do, let me introduce my co-host. Now, Carol Christian usually does these with me, but she is out, and I know we're all going to feel really sorry for her, but she's in Venice right now setting up a Hubble exhibit and could not attend this week. And I tried to convince her to do the hangout from a gondola, but I couldn't do that out. But anyway, filling in for at least a brief time is my good friend Dr. Harley Thronson from NASA Goddard. He's an astronomer, and he also joins me for the Footsteps to Mars and the Future in Space Hangouts. Hi, Harley.
Hey, good afternoon, guys. Happy to step in for somebody like a Carol who's doing such hard duty.
Yes, I know. We just take your
so here I am from Alexandria, Virginia.
Yes, I know. So anyway, so she'll be back next time, but for now she couldn't make it. So we do these hangouts, in case you weren't aware, something we do to help you kind of get behind the scenes to a lot of research for members of the American Astronautical Society and the members of the American Astronomical Society. Both organizations endorse these hangouts. And while the hangouts themselves are endorsed, the views and opinions expressed by our guests are not necessarily endorsed by them. But we needed to make that distinction anyway. So, in every single week, we pick a paper, or Carol picks a paper, and invites the guests to talk a little bit more about it, because this is something that happens in astronomy organizations and universities across the world. They get together once a week and they have coffee and they talk about astronomy and the latest research. And so that's what we're going to do here today. And before I introduce my guests, I want to also let you know that while this is sort of a replica of what goes on in astronomy departments around the world, it's not necessarily the same, because this is a social media event. We want you to get involved by asking questions and comments for our guests. And the two main ways you can do that is with the live chats that I have set up on the YouTube webpage, as well the channel page where this is being streamed, also on deepastronomy.com/live. I have a chat client going, and people are, and as music, I'm looking at on Twitter, so please feel free to leave. I'm monitoring all three of those. Okay, so today it's about black holes, and in particular, our guests today have been doing some interesting research using data from the NASA NuSTAR spacecraft, which is the nuclear spectroscopic telescope array. That's what NuSTAR stands for. And so there's a lot of, and they use it primarily in black hole research. We're going to find out how they're doing it. And the lead author on our paper, I want to introduce him first, is Adham El-Batal. He is a PhD candidate. Hi, Adham. He's a PhD candidate at Boston University, and he's the first author of this paper that we're going to discuss. But I just want to mention at the top, and we're going to hear his story in just a little bit later. He was an undergraduate when he did this research. And so that is very exciting. And I want to talk a little bit about how he was able to do that. And also with me is Dr. John Miller, professor of astronomy at the University of Michigan. And welcome, John, first off.
Hi, how are you?
Were you his advisor, or did you just work with Adham while he was doing the research on this?
Yeah, I was Adham's advisor, but in our group, things are really fluid. So we work together, really.
I really want to talk about that dynamic, because right now I'm in the middle of some blog posts about going to school in astronomy, and I want to talk about your story after we get done here a little bit. But before I do, let's go ahead and get started with this paper itself. Adham, let's go ahead and start with you. Can you give us first of all a brief summary of the research you did, and then I want to take a step back and we're going to talk a little bit about some basics of black holes. So tell us briefly about some of your research. What is this paper?
So the object we were studying is GS 1354-645. That's just,
oh yes, my old friend,
coordinates. It's essentially a black hole and a star revolving around each other. And in the process, the black hole has a strong gravitational pull. It sucks in material from the star. And that material accretes around the black hole. It forms a disk around it. that material glows, and by observing the light from the disk, you can determine information about its properties. And what we did was we observed this black hole during an outburst, which is a period when it goes really bright. What we observed was a spectrum that told us some information about it. And by fitting models to it, we were able to determine certain parameters of this black hole, like its spin. And what we found is that it's very rapidly spinning. Black holes rotate. They have some spin.
Okay, well, thank you for that. And have like a little bit about what you're talking about. This black hole, this is a schematic of the kind of black hole that Adham was talking about. These are stellar-sized black holes, right? Meaning that they are roughly the size of a star.
They're roughly the mass of a star, yeah.
Okay, so here in this case, this is a black hole that's near a neighboring companion star, and it is pulling material off of that star onto an accretion disk. And as you can see here, there are these jets that come out. These are very high energy jets, aren't they, Adham?
Yeah, they're very bright, very energetic.
They come in, so as the material swirls in, they come in and they accelerate this gas and dust, and these jets are one of the products of it. Now, one of the properties of a black hole is that it spins, but that's not its only property. It is also, for those of you who don't know what a black hole is, there are two main types. One are stellar sized, and they result from the death, like this one, like this GS 1354, and they generally happen when a star dies. They are the remnant of a stellar, so either a supernova or the death of a star. And then there are also supermassive black holes, which are several 100 million times larger than a stellar star. Those are typically found in the centers of galaxies. And so what we're talking about here are stellar-sized ones in particular. So we have black holes that are, and they are extremely massive. They're very dense. They take up very little space, which means their gravity is very strong. Adham says they spin. What are some other characteristics of black holes?
Well, black holes are, there's this theory called the no hair theory, that there's no hair on them. They're very simple. They can be described entirely using their spin, which is how fast they're rotating, their mass, and their charge. Is that right,
Charge,
John?
electrical charge?
That's correct. We don't think that black holes that really exist out in space have any charge. The black holes that exist only on paper can have charge, but the ones in space we think are electrically neutral.
Why is that? Why can't they be? Why would they only theoretically have a charge?
We think that almost any setting in which you would put a black hole in the universe would encounter enough gas and enough particles that it would tend to neutralize its charge in really short periods of time.
So to get a charge in the first place, and then I'll leave this topic, but I'm trying to visualize it. Black holes are sucking things in. Among those things it's sucking in are charged particles. There may be a period during the time of doing that where it's gotten slightly more electrons than, say, protons, and it might be temporarily charged, but as soon as it sucks in more stuff, it might neutralize. Is that
that's right. We think on really short times it would be completely neutral. So
there might be a time when you look at it, say an instantaneous, it might have a charge, but overall it's going to neutralize itself out.
Right.
Interesting. Okay, cool. All right. Well, I guess we've alluded to this, and this is again part of our basic discussion on black holes before we get into the research of Adham here. But so black holes, they spin, but they're black. They don't let they're so powerful, the gravity doesn't let anything escape from them. What are some of the best ways of seeing these things? How do we even see them at all?
Usually, well, what you do is you look for something in their vicinity. In the case of this black hole, it's pulling in material from its companion star, and that material is visible and it glows. So that's how we observe this. And more recently, some scientists have started using gravitational waves to detect black holes.
Ah, yes. Okay, that's right. That has to do when two black holes merge, and that we've talked about that many times on this before, where we had the
LIGO folks.
The LIGO folks on. That's right, where they talked about the ripples that are generated in space-time around this. So in this schematic, we have the visible waves, or the high energy waves. You can see it through X-rays, with material that's swirling around the black hole itself, getting accelerated, emitting a lot of high energy radiation like X-rays and things like that. These jets are very strong, gamma ray and higher, right, John?
That's right. The jets are likely contributing at every wavelength. I think we mostly managed to detect them in radio bands, actually.
So also the bright in radio too. Good.
Yeah.
Okay. So these are another way, but there's another way you can see them using gravitational waves, like Adam said. But there's also lensing, gravitational lensing, right? When the black hole moves in front of or in between us and a background star or galaxy, we could see it. The gravity influence change that distant background object, right?
Yeah. That would need a particularly massive black hole, though.
Oh,
right?
good. So you can't really do this with. Well, can you do it with stellar-sized black holes?
Can you, John?
It's just that you can't resolve the flux enhancements because they're very small. So Adam is correct. The best way to do this is with very, very massive black holes.
Okay, so but it is another way in which we can see them. So okay, so now I want to set the stage for your research, Adam, and that is on the idea of rotating black holes. Now, I came across this before while I was doing some poking around before you guys joined, and I found this little cartoon here on NewStar's website, and it talked about different models. This was different models for how black holes rotate. And I was wondering if one of you, and I'm not sure which one would be most appropriate, to talk about this schematic a little bit for us. Tell us what it means. John or Adham?
John, do you want to do it?
Sure, no problem. So the way we measure black hole spin is we use the material that's flowing around the black hole. And spin has this funny effect. When matter is orbiting a black hole that has no spin, the crucial radius at which matter falls in and will not escape is larger than in the case where the black hole spins. When the black hole spins, material can orbit more closely around the black hole than otherwise. So that means that it's moving faster, and we use the spectra in X-rays to try to measure how fast the gas is moving. And because there's this direct relationship between how fast the black hole spins and how close the material can get, the speed of the material basically ends up telling us the spin of the black hole.
Wow. So in this cartoon here, the middle one, there is a case where the black hole itself isn't spinning. These arrows talk about the accretion disk rotation, the material falling in, but the
Right.
black hole itself in this case is not spinning, and you can see that there's a distance here between the event horizon and the I don't know what you call that, in the inner part of this accretion disk. In the lower case, you have it where is prograde, where the direction of the rotation of the black hole is the same as the accretion disk.
That's right.
Okay, and so as you were saying, things get really super close. But in this top case, the black hole's going the other way.
That's right.
And boy, it's really just is spreading out a lot of that material, and presumably slowing it down, right, John?
I don't think that it's sort of actively. I don't think it's acting like friction, I would say. It's just that the material inevitably falls in to the black hole, starting at a larger radius.
So what are the forces? Is it a gravitational wave force that is causing this to happen? I mean, the material as it falls in has to overcome this something. What is that force that it has to overcome in the rotation of a black hole?
This is
going the other way.
This is general relativity. When we think about how planets orbit the sun, the the orbits are all relatively simple until you get to, say, Mercury. But around a black hole, there's a radius outside of which things can orbit in normal circular orbits, like Kepler described, and a radius inside of which matter will inevitably spiral inward toward the black hole. And so this isn't something that requires gravitational waves, but what you're getting at here is one of the differences between general relativity and Newton's flavor of gravity. So that cartoon is kind of a stark depiction of this special radius around black holes that depends on their spin.
Okay. And so I guess, should we talk about these little bits here off to the right? What are these graphs? These are X-ray brightnesses, so versus energy. So different particle energies are being plotted versus their brightness, and they seem to have these characteristic shapes depending on the situation that you have here, whether you've got prograde, no rotation, or retrograde rotation. So this is how you see, or is this the main way? Uh-oh, is that you, Harley? Yes, he's having another cat attack. We're gonna make those guys our mascots. Okay, so is this the main way, John, that you would see? Or is this a main indicator of a rotating black hole?
This is it. So when the disk is kind of glowing in X-rays, if you like, and there is some iron in that disk of orbiting gas, and the iron glows, and on that scale that you see in these figures, the iron line is at 6 to 7 keV. That's thousands of electron volts. And when the material moves faster, Doppler shifts, basically the train whistle effect, end up spreading the iron line over a wider range of energies. So when the line looks like it's really wide, that means that there's a broad range of speeds. And when the line is very narrow, it means that there's a smaller range of speeds. So when it's wide, that means the material gets to go very close to the black hole before it falls in, and that means the black hole is spinning.
Got it. Okay, thank you for that. Okay, so we have set the stage. Let me stop this. We have set the stage for what we're going to talk about now, which is the paper that Adham and John have come out with, among others. And so we know a little bit about what black holes are. We know about some of the properties and the fact that they spin, and sort of how you can tell they spin. So Adham, tell us what you were doing here with this paper. What is your what was the work you had done, and what did you find?
Sure. Can you pull up the Swift curve?
I sure will. I believe it's this one. Is this the one?
It's loading on my side. That's it. Right.
Okay.
Okay. So what happens is you need the black hole disk, the disk, to be bright enough that you can probe the inner parts of it, because that's where it's most affected by the spin. And so you need a black hole that is bright. And for that, you usually wait for it to go into outburst, which is where this came in. So Swift is a satellite that probes gamma ray bursts, black hole binaries, energetic stuff, continuously. And if you look on the horizontal axis, that's days.
These are days down here.
So yeah, this is observing the same object over a period of 300 days. And there's a period in the middle where it's clearly brighter. It notices that. And so John got time on the New Star satellite to observe it during that time period, which is shown by the two dashed lines. Each one of those was an observation that we did. The brighter one is the one to the right, because that shows a higher peak.
Wow, so you guys got time pretty quick into this, because this was like, what, 50, I don't know what these are, 50, 60, 70, 80 days in. You guys got time from 80 to about 115 days. That's pretty cool. And it's like right after it started to go up, right?
Right. So yeah, so we got the data during that, and if you can pull up the New Stars spectrum that I sent.
Mm-hmm. Okay.
Okay, so the new star spectrum is what we actually observed. When it says energy in the horizontal axis, that's another way of saying wavelength. So at that specific observation, it emits a broad range of fluxes across wavelengths. And the red dots that you see in the upper panel, that's the data. That's from new star.
Okay.
We got that data. And the blue line that's running through it is a model.
Really?
Yes.
That's pretty darn good.
It's really good. It was shockingly good. So the blue line, you create a model that you use to try to recreate the same spectrum that you observed. And that would hopefully tell you the physical properties, because if you can make it knowing the parameters that you made it with and it fits the data, then hopefully that describes the data accurately. And so you tweak parameters until it works. And the bump that you see near the beginning, that's the what's called the iron K line, which John talked about earlier. That is a good probe of the spin. So the program that we run fit the model to the data until it works. And that told us that it's spinning at, I think it was 99.8% of the maximal spin, or 98%.
What does that mean, the maximal spin?
Well, the maximal spin is, and John can correct me if I'm wrong, it's the point, theoretically, where the black hole is spinning so fast that the event horizon disappears. You would get a naked singularity.
Wow, really? So that's what that is. Okay.
I don't think that's physically possible, right, John?
We sure hope not. I believe the answer is no.
It would violate causality. So this is 98% of that. Pretty confidently so. So yeah, that's pretty much.
So basically, that means it's spinning really, really fast.
Yes.
Okay, I don't want to leave this naked singularity thing yet. Why don't we want to see that, John?
Well, Adham was right. If you had a naked singularity, you could do an orbit around the naked singularity, and that would violate causality. You could theoretically go back in time if you did so. We think that's forbidden by every law of physics that we know. So it seems like a good bet that's not going to be the case here either.
And what was the term you used again? Maximal, what was it, Adham?
Spin.
Maximal spin. And that is this point where it's spinning so fast that you just have no event horizon whatsoever.
Just a naked black hole at the center, yes.
Okay, so am I the only one having trouble visualizing that? Because I have no idea. I know what an event horizon is. I know that that's the point beyond which you can't escape a black hole and that all kinds of funky, strange things happen. But to not have it at all is related to how fast it's spinning. I mean, if you wanted to, does the event horizon, like the accretion disk, go up and down based on its spin?
Yes, it does.
Okay.
The event horizon, depending on how fast it's spinning, can range from a few kilometers to much closer than that. And so yeah, if the event horizon, the point from which no light can escape, that changes depending on how fast the black hole is spinning. And a hypothetical black hole that's spinning at 100% has no event horizon.
Crazy.
What about you, Harley? You got anything to add to that? You sit there. I see you.
I was doing research.
You're going like this.
Great research. It was formation of. I did stellar formation of solar mass stars. This stuff gets pretty exciting. Maybe a way to describe this would be, guys. Could you describe the event horizon, the location, maybe nature, but the location of the event horizon as a theoretical, as a model black hole spins faster and faster and faster? Does the event horizon physically close in on the black hole, and it disappears in the sense of it, this is the wrong word to use, merges with the black hole? What happens to the black hole at, say, 95% of that speed? 6 and so on.
Getting really close to 100%, well, a black hole that is not rotating would have a event horizon that's about 9 kilometers outside of it.
Okay.
That would be the point from which light cannot escape.
Right. Right.
In the most extreme, physically possible situation, it's about 1.5 kilometers. So there is 1.5 kilometers boundary between the actual black hole and what you can see. In the maximal hypothetical spin, that boundary does not exist. The black hole is just sitting there.
And in the case of what this graph that you have, you said it was 90 what percent?
Between 98 and 99%.
So this is really close.
Yeah, it is.
To that point. So this thing is spinning really, really fast. I mean, wow. Did you believe this at first? I mean, so I know you have this model that the blue dots, and then you said you had parameters in that model that when you tweak them, it tells you certain things about the properties of the black hole itself. What is this unusual? Is this do you think there's a lot of these? Or have you seen?
There are a lot of. I think every black hole spin measurement so far has been 80% or higher. But this is the highest so far. Is that right, John?
Certainly among the highest couple. I don't know exactly which is the highest, but this is clearly as high as one would hope to go.
So that was actually going to be my next question, which, I mean, how rare, and you're getting to that now, how rare is this? And apparently it's pretty darn rare.
There are a few of these measurements so far. They have all been relatively high spin historically. 80% and above has usually been the range.
Okay, so let's talk a little bit then about NuSTAR, because this is where these measurements were taken. What kind of instrument is NuSTAR, and do you expect to see, will it allow us to get a bigger survey or sample size of these black holes to get a better handle on whether or not this is very rare?
John?
Well, NuSTAR is a special kind of X-ray telescope, which is a special kind of telescope anyway. So to observe in X-rays, we have to get above the atmosphere. The atmosphere is really good at screening out X-ray light, which is very fortunate for us, because obviously we don't want a lot of X-rays hitting us. So we have to do X-ray astronomy from orbit. And if we think about a normal telescope mirror as being sort of a large sheet of glass and things reflect off the mirror, you know, almost 180 degrees, the way they do when we look at our own image in a mirror, X-ray light has too much energy for that to work. X-ray light would just go straight through a mirror like the ones we use in our normal optical telescopes on the ground. So X-ray mirrors have to be conical shells. That's maybe a little bit hard to envision, but if you think about sort of a stack of red plastic cups, it's almost like that, but they're hollow at the bottom, and the light gets nudged by the very gentle slope in these nested mirrors, and you achieve a focus. Now, we've been able to do that with sort of lower energy X-rays for a couple of decades now, but we haven't been able to do it in hard X-rays. And the real advance of NuSTAR is it's getting a focused X-ray image an order of magnitude higher in energy than has been possible before. And there's a lot of technology that goes into that, but partly it's how you construct the mirrors and how you coat them. And partly it's how you construct the telescope. And when you look at that picture of NuSTAR, maybe the thing that stands out is that there's a boom. And this thing is sort of two modules separated by that huge set of lattice work. And that's why NuSTAR is able to do the special trick of imaging really nice energetic X-rays, because it has this long boom and a long focal length. And so this is a very special instrument. And as you were alluding to a moment ago, we do think that NuSTAR is likely going to add greatly to the number of black hole spins that we have measured. It's a really well-designed telescope for this purpose.
And it looks to be the way you use it is much like you use Hubble, right? You apply for time, and then you give the science case for wanting to observe it, and then it points and shoots, as opposed to, say, a survey telescope. That's what I'm getting at. So you have to tell NuSTAR where to point and where to go look, right?
That's exactly right.
Okay.
And they do one thing that's even a little more special besides. Since the X-ray universe is one where things happen quickly, as you could see in that graph from the Swift telescope that Adham showed a few minutes ago, NuSTAR has to be able to respond to requests to observe something the same day, or sometimes even within a couple of hours.
I know, it was remarkable. You guys got observing time really fast. That was before you were on the leading edge of that curve that was going up. So you got it really early.
They are tremendous in their ability to respond to requests like that.
So am I right? I don't know if you can see my mouse pointer, but if you're pointing at something with NuSTAR, the object might be over here. The X-ray light would come in through here, reflect off, hit this secondary, and then come down again to the instrumentation here. Do I have that right? The path?
I believe that the instruments are on the back end where the solar panels are, and the mirrors are the deployed out on the boom.
I see. Okay, so I give it a shot. But I mentioned earlier to reflect and focus X-rays is extremely hard. And when we had Steeple and Chandra X-ray telescope on board, they had these long cylindrical cones gently try and focus X-rays, but it's very hard because X-rays go through stuff, and it's hard to focus them. So NuSTAR is doing it is a point out a sort of point and shoot mode. As you see these increases in energy coming off of different objects, you can look at it with NuSTAR and get these things and get these characteristics of hopefully more energetic black holes. So that's NuSTAR. Adham, what was the data like? What did you get from the telescope when you go? Do you get an image? Do you get a stream of numbers? What do you get from the telescope?
You get that spectrum that I showed you, but it was actually John who reduced the data. So, John, can you talk more about the reduction? Because I wasn't part of that.
So
I'm going to put it up again while you talk.
Okay.
Okay. So this is a spectrum then.
Yes.
Okay. And okay. So how is this for the handling an image?
I'm terribly sorry that broke up for just a minute. Could you repeat it?
Oh yeah. Okay. So this is a spectrum that Adham used to determine the spin rate. How was processing X-ray data different from an image, or is it an image?
So we also get an image, and so you can see a really bright source in your field of view. And in this case, it's so bright that it's really the only thing that you can see in your field of view. It swamps any other X-ray sources that the detector might have seen otherwise. It's a very, very bright source for a telescope like NuSTAR, but NuSTAR can handle that situation. And when we get X-ray light, we can also dice up the light and examine the distribution of energies that the light had when it hit the detector. And so that's what we've done in that plot there. And what we're really looking for is the special energies where we detect iron in emission. And so again, it's the width of that iron feature that really does most of the work to tell us what the black hole is doing.
This little blip right here.
That's right. And if you remember the cartoon we discussed at the start, when the line is very sharp and peaky, the black hole likely isn't spinning very fast. And our data looks most like the cartoon spectrum at the bottom right.
Yeah, I see.
The line is quite spread out because it's originating very close to the black hole.
Okay, so what's this little blip here? That little gravitational distortion. Is that relevant to what we're talking about, or is that just something else?
I think
I don't see that in this.
In that idealized realization, it's assuming sort of perfect spectral resolution, which we never quite have.
Okay.
And that's a that's a peak owing to very, very strong Doppler shifts. So that little peak would have corresponded to light that was directed right into your line of sight.
I see. Okay. All right. Well, I have a good question that I think is relevant to exactly what we're talking about here. And this is from Alexander Honcharov from YouTube. He's asking, how do you know / find out the direction of rotation of a black hole? Does this tell you anything about the direction of the spin? You've already given us some idea about the rate.
Yeah, if you can go back to that cartoon again.
Okay.
It's the prograde versus retrograde motion.
Right.
Prograde means it's rotating in the same direction as the disk, and so that's when you get that shape. And retrograde is rotating in the opposite way, and that's when the accretion disk gets pushed farther away. So that's how you can tell whether it's forward or backward motion.
So slower spinning retrograde black holes will have this real tight peak, but faster spinning prograde black holes will give you this longer one, like what you observed, right?
Right.
Now, how important of a role? So really, you can't see this at all without some kind of accretion disk, right?
Yes. You need an accretion disk for this.
So if the black hole isn't feeding, you don't see anything.
Yep.
Right?
That's right.
Okay, good. So that's an important point to remember. Andrew Planet is asking on the live chat, do these black holes spin because the gravitational... Try that again. Do these black holes spin because the gravitationally inbound accretion disk is polarized, as in a north and a south? Are they polarized at all?
Well, the black hole, as far as I know, spins because it comes from a spinning star. Stars rotate, even the sun does.
Mm-hmm. Once every 27 minutes.
And there is the conservation of angular momentum, which says something that's rotating, if you shrink it, will rotate faster. Something like a figure skater. Figure skater is spinning, closes their arms together, they spin faster. So if you have a star that's rotating, when it collapses into a black hole at the end of its lifetime, it's collapsing into something much, much, much smaller. So it speeds up its rotation. That's where the black hole spin comes from for a stellar mass black hole.
So can you use the standard physics analogy of a figure skater spinning and pulling her arms in, spinning faster, the conservation of angular momentum example in this case?
It's the same physics, essentially, yeah.
Same thing. So yeah, so the spin comes from the initial star spin itself, which black holes tend to come from the deaths of stars, supernovae in particular, but they maintain their spin, which I think is really cool. Where was that question? Shoot, I just had a question. This is from Hans Milling. He's on the live chat. He's asking, how can the matter in the jets, this is from those jets we were talking about, escape the black hole? Is it because the matter in the jets never crossed the event horizon? What are those jets, first of all, and how can they escape?
John, do you want to do that?
The answer is that the matter has not crossed the event horizon. So the person who was asking that had exactly the right intuition. We think that jets are likely powered magnetically. The disk of gas that's falling into the black hole is very hot, so it's ionized, and that means that we have lots of charged particles orbiting very quickly. And you know that when we have a current, that we can create a magnetic field, and we think in rough terms that this has something to do with how the jets are being launched. So the material is being shot out, we think, by a magnetic process. And to be very honest, this is something where we do not yet have a handle on the details observationally, and lots of teams are working on that very problem. But it's very likely that the jets have some population of electrons, and how many protons they have in them is uncertain. But my own guess is that they aren't loaded very heavily with things like protons, because they're so much more massive, and that means the energy required to power those jets goes up by orders of magnitude. So I think it's safe to bet that they have a population of electrons and very few protons.
Yeah, it makes a lot of sense, I suppose, because stars, like our sun, have a lot of plasma or charged particles running around in magnetic fields, and it makes sense if you're going to suck that stuff off of a star, you're going to get a lot of charged particles running around in here, and whenever you accelerate those charged particles, you also get a magnetic field. So it's really quite astonishing the dynamics that go into these, and just how amazing a black hole that's feeding looks versus one that's just sitting out there in space. They're actually quite boring, I guess, if they're not eating something. The one, for example, in the supermassive black hole center of the Milky Way is currently quiescent. It's not eating something, although I think a gas cloud is on the way for it to be devoured soon. So there's a lot of difference between a black hole that's feeding and one that isn't. Okay, so Adam, you did this research. This isn't relative. Right now, you're a PhD candidate at Boston University, but you did this research when you were an undergrad, right?
Yes, that's right.
So I was a physics student at the University of Colorado, and I can tell you flat out, it was hard. I worked hard at it, and I didn't have any time to do anything but what my professors told me. Tell us the story behind doing this as an undergraduate. I think that's a fascinating story.
Well, it started the summer before my senior year, so I wasn't taking classes for a few months. I was looking for a research project, and I got in touch with John, and he had this new star data, and he essentially gave it to me and gave me the software to work with it, and he told me, run with this, see what you can get. And so I used this software called XSpec, which is neat software for analyzing data of high energy astrophysics. And you take the data and then you try to fit a model to it, and the program will run the parameters to try and get them to fit the data. So that was okay, it worked okay, and I remember was in a group meeting with John when I showed him the results of the fit, and his only reaction was, "Huh." It was spinning very fast, and the fit was really good, and nature's not usually that kind. So the following few months was me forcing the program to try and fit the wrong parameters and see if it comes back to the same numbers again, to avoid any anomalies. And time again, it came back to the same values. So it was pretty confident that that's what's going on. So yeah, that was the chunk of the summer. And then during the academic year, I was just writing up the paper that got published after that.
So John, you gave him the data, and you got it presumably from some time you had on NewStar. Did you have any indication that you were going to be finding one of the fastest spinning black holes ever?
No, we had no prior indication, but I was. And
it doesn't sound like you were that impressed. You're like, yeah, whatever.
Well, it's not that he wasn't impressed; he was shocked.
Oh, is that okay? I took the hunk to mean, oh, okay, whatever.
And it's one of those things where, when you see something that in some way you would like to see, you know that the road ahead is going to be very difficult, because you have an obligation to try very hard to prove that wrong. If you're going to dare to believe it in the end, you have to work very hard before that time to test it and make sure it's right.
I feel you, because here I'm looking at red lines and blue lines that look really, really good together, and I can definitely see your suspicion. I would be suspicious of that too. So the blue, just to remind everybody, was the model that Adam used to, and the parameters, and the red is the actual data. Now,
if you look at the lower panel that says ratio, that's essentially the data divided by the model. And if they fit, it should be 1. And you can see it's extremely close to 1 almost throughout.
So why does it get wonky out here? What happens out here, do you think?
Resolution's kind of low in that higher energy regime with the data.
Okay, but this is the part you're interested in anyway, right? This part where the iron happened.
Yes.
Anyhow. So yeah, that's a pretty darn good agreement. So John, and I guess both of you were pretty skeptical. So you spent the summer out on getting just trying to make it wrong, or to see what else it could possibly be. But you know, when you said that, a red flag kind of went up. How much do you trust this software? First of all, who wrote it, and why are you sure that are there any other tools you could have used besides this software package?
The software was written by high energy astrophysicists several years ago. The model we use is called Reynolds. Of course, there are caveats to it. But in terms of models for modeling a relativistic accretion disk, it's as good as we get right now. What other tools are there, John?
So I guess the way I would say it is that the package that we use to process and fit those spectra was developed decades ago. The original author is a brilliant scientist named Keith Arnaud, and he and a small team worked very hard on that software at NASA's Goddard Space Flight Center. And the entire high-energy astrophysics community uses that software, and we talk amongst ourselves, and we talk at conferences, and when bugs are identified, they're reported to the whole community, and they're quickly chased down. So there's a large community of people who are using this software and vetting it continually. The particular model that we used has a long heritage as well, and although it's newer than the package that does the statistical tools, the spectral model that we used is, again, robust and being tested by a large number of X-ray astronomers. I think it's used every single day, and it appears in the literature, if not daily, then nearly so. So one always needs to be skeptical. That's the nature of science. But we think these tools are fairly robust.
And in the bottom panel, I see these vertical lines, which presumably are error bars, correct?
That is correct.
Yes.
Okay, this is how much you know, or an estimate of how much you know, how confident you are in your measurement based on the data. These are there's error bars here too. They're just very small, aren't they?
On that scale, they seem very small.
Okay, so those are pluses, and as they do get larger up here. So okay, there are error bars there as well. So wow. So as long as you can get your blue lines to match your red lines, you think you're onto something there, folks, because that is the model. And I've mentioned this before in several vlog posts and things like that. There are models everywhere, but what we need are sets of observations like new stars to help us decide which models best describe what we think is going on out in the universe. And here's a prime example of this. Here's a model that describes spinning black holes, and NuSTAR goes out and takes some data that have relatively good high quality resolution, and Adham goes and fits that data to the model to see how well it matches, and he found that it worked out really, really well. So, and he just happened to find one of the fastest spinning black holes that we know of. I have a question about supermassive black holes. Do they spin? Can they spin this fast? These are black holes that are millions of times to billions of times larger than our sun, the mass of our sun. Can they spin this fast?
John,
Yes.
I think that's best. Yeah.
Yes, they can. And NuSTAR seems to have found the fastest spinning supermassive black hole as well.
Really?
That was one of its premier early science results. Yes.
And is this like in kilometers per second? What's the units for spin? Revolutions per minute, per second, per?
You could do it that way if you wish to. We don't do it that way. It's a thing that we've normalized, and it's a dimensionless angular momentum that we measure. We call it A, and A can be between -1 and 1. So
with 1 being really fast,
maximally prograde.
Okay,
and -1 being maximally retrograde compared to the matter that's falling in.
And 0, no spin at all.
Right.
Okay. Galaxia had a comment here. Where'd it go? Oh, her comment is on the live chat, and she's commenting that maybe she's talking about the spin of the black hole and its age. She says maybe this means that this is a very young black hole since it is spinning so extremely fast. Is there a relationship between the spin rate and the age of a black hole?
In the case of stellar mass black holes, I believe the answer is likely no. So the stellar mass black holes, they might have a mass of, say, 10 times the mass of our sun. And the companion star from which they're getting some matter is only about the mass of our sun. There simply isn't enough matter to transfer onto the black hole to change its spin by a large fraction. In the case of supermassive black holes, however, the amount of gas that's available in a galaxy to fall onto the supermassive black hole can be many times greater than the mass of the black hole itself. And in that case, the fall of matter onto the black hole can change its spin completely.
Wow. Okay. So I'm looking through the chat here, and Hans Milling is asking a really good question. Let me just read this here. Can you conclude anything from one event or chart? I guess you need some more observations to confirm everything. So here we have one example, one set of data. Do you need more observations from other examples to feel more confident that this is what you're seeing, or is one enough?
Well, for this one, it was actually two observations.
That's right.
The one that you brought up, that's the brighter one. If you recall from the Swift curve, there were two lines, two dashed lines. The one you're looking at is the brighter one. There was an earlier observation that wasn't as bright, but the spin value agreed. Pretty much. I just didn't copy that picture because it was a little redundant. It was more or less it's very similar.
Sure. So that is a good point, though, Hans. You want to definitely get more observations if you can, whenever possible. Let's see. Andrew Planet. Hi, Andrew. It's good to see you again. Does the black hole entirely spin independently from the incoming accretion disk, or both at the same time? So are the spins of the black hole and the accretion disk independent? Are they tied somehow?
It's hard to think of exactly the right way to phrase the answer. So the material that's falling in does not much affect the spin of the black hole. If the black hole is spinning very rapidly, the orbiting gas gets to be a little bit closer to the black hole before it falls in without any chance of escape. So in that way, a spinning black hole does allow material to spin faster before it really falls in. So they're linked, but if the question is asking, are they sort of linked a priori? Is the gas inevitably going to reach a certain speed right before it falls in? It depends a lot on the details of the infall, let's say.
Yeah, and I guess I don't know, maybe it's a mistake to do this, but I always think of it as black holes as being one big drain, and so of course as things go into a curved space-time like that, it would start to spin, but that could just be me thinking too simplistically. It just maybe sometimes these visualizations that we come up with are a little misleading. So, but yeah, I guess it's a very complicated thing to think through for sure. Let's see. There's a lot of comments on that. You guys are chatting amongst yourselves on YouTube, which is good. You're having a good conversation. And Adil is asking: is a black hole's entire mass in its center, or is it massless? Black holes are kind of a strange thing because they are infinite volume or zero volume and infinite density. Is there a way to characterize where most of the mass is in a black hole? I'm not sure that makes sense.
Somewhere inside the event horizon.
Yeah, that's all you could say, isn't it?
Okay. But they're not massless for sure. They have mass.
Yes. Otherwise, there wouldn't be a gravity well there. Let's see. And George Caldwell is asking a question about quasars. Are quasars more likely to form around fast-spinning black holes? Quasars. First of all, we should talk about what they are. What are quasars, John?
Quasars are kind of the scaled-up version of the black hole that we looked at. So our black hole was, we think, 10 times the mass of our sun, and quasars can be 10 million or 100 million times the mass of our sun. And when they have a disk of gas around them, and we say that's when they're accreting actively, they can release tremendous amounts of ionizing radiation and very powerful jets. And in those instances, around quasars, the radiation can be so intense and the jets can be so powerful that they can, in fact, reshape their host galaxy and start to influence the evolution of that galaxy, which in turn influences the evolution of the black hole that powers the quasar.
Yes, and here's a sort of a schematic that I got from the New Star website on a supermassive black hole. The only thing really different here is the size, and you can see that the background has been distorted a bit with the gravitational lensing. There's an accretion disk here, and this big jet coming out presumably would be that of a burst of a quasar. This particular bright thing was was part of a discussion of a corona, and I don't know really what a black hole's corona is, but that's what that's supposed to symbolize. But yeah, this is a supermassive black hole. Now, are they more? So then, to get to George's question, do you think quasars are more likely to happen, these outbursts, with spinning black holes?
When the black hole has a higher spin, it can be brighter, and it can launch more energy. So the spin doesn't make a quasar more likely, but it makes a quasar more potent. Maybe that's the best way to look at it.
Okay, good. And he's got a follow-up on that same idea, which is about spinning black holes and Hawking radiation. Do they emit Hawking radiation at a faster rate than non-spinning black holes of the same mass? And you should probably tell us what Hawking radiation is.
That's a fascinating question. I will admit that I do not know the answer, and I have not thought about that, but I will get on to that because it is a terrific question. So well done.
Way to go, George. Yeah, our viewers, they've often done this. They ask really good questions, and this has happened before. So yeah, spinning black holes and Hawking radiation. First of all, Hawking radiation. It's this idea of these antimatter particles. One of the two pair gets sucked into the event horizon. The other one does not. Am I giving that justice, or am I just tearing it up?
I think that's exactly right. Yeah.
Okay. So Hawking radiation is this, and what effect the spinning black hole has on that emission rate. You got him, George. So I guess we'll stay tuned. All right. Well, thanks for that. That was a good question, George. Thank you. Let's see. Okay, Rainbow Panda. Do black holes ever temporarily form accretion spheres instead of disks? Is it always got to be a disk, or can you get any other kind of shape?
I believe intermediate mass black holes can form a spherical, can accrete matter spherically. Right.
Now, these are black holes that aren't stellar size. They're more than stellar size, but they're not supermassive, right?
Right.
Okay.
I think that what matters is how much matter you're trying to dump onto the black hole per time. So if you're gently sort of showering matter onto the black hole, there are models that suggest that it can be more spherical. But if you're putting a lot of matter onto the black hole so that the matter interacts with itself, then there will tend to be a net angular momentum, and then you will develop into the matter will develop into a disk. So it matters how fast you're trying to pour matter onto the black hole.
All right. Well, guys, I'm almost out of time, and so I'm going to have to cut it off here. I've been meaning to, I got so caught up in the discussion, I forgot to let you know that you are listening to an Astro Coffee Hangout, and my guests are Adham El-Batal he's a PhD candidate from Boston University, and the first author of the paper that we've been talking about on the spinning black hole. Also with me is Dr. John Miller, professor of astronomy at the University of Michigan, who worked with Adham when he was at Michigan as an undergraduate, and they did this work together, and the paper came out in Astronomy and Astrophysics, or was it APJ? I forgot to.
It was Astrophysical Journal Letters.
Astrophysical, yeah. So it was APJ. So and this just recently came out, and I want to thank you both for doing this. Adham, give us what are you working on now? You've done already some pretty good work as an undergrad. What are you doing now? What's your PhD candidate? What are you studying?
Currently, I'm working with Professor Dan Clemens at Boston. He is looking to map the magnetic field of the galactic plane, the Milky Way's plane. And he does it by looking at how light is polarized. Essentially, light can be aligned in a certain angle, and that can tell you a lot about the magnetic field of the Milky Way. And so the project he has is an ambitious project to try and map the whole thing.
Yeah, that is ambitious. I'd love to see that. That
Yeah,
sounds like
currently-
a hangout. That sounds like a hangout. I wonder if I can get you guys to talk about that next time. All right. Well, I want to thank you both for taking time out to talk to me about this paper, Rapidly Spinning Black Holes. They found one of the fastest spinning black holes ever. And I want to thank you both for taking time out to join us. And I hope you'll come back when you have some more stuff to share with us.
Thank you.
Sure. Thank you very much.
All right, great. So, all right, guys, I want to thank you all for watching. Next week is our Footsteps to Mars hangout. Harley will be back. Harley had to leave. He could only stay for about a half an hour this time. And we're going to be talking about getting to Mars and putting resources up in orbit and using them on the way to Mars and how that might help us out. We've got guests coming in from, I think, from Jet Propulsion Laboratory and other places in NASA Goddard to talk about getting us to Mars and getting resources stationed along the way. So that's next week. Thank you all again very much. On behalf of Carol Christian, who could not be here, she's in lovely Venice right now. Carol, you're gonna have to tell me how it went when you get back. Anyway, I hope you guys will join us next week. Thank you all very much for watching, and as always, keep looking up.